The second colligative property, that is elevation in boiling point. So the boiling point is the temperature at which the vapor pressure of the liquid becomes exactly equal to the atmospheric pressure. When the vapor pressure of the liquid becomes exactly equal to the atmospheric pressure, the liquid begins to boil. That is, the liquid molecules start converting to the vapor phase. So let us see what is the effect of the addition of a solute molecule to the boiling point. So for that we have to understand this diagram. So this diagram is actually a plot of the vapor pressure versus temperature. So here we can see the curve AB, which is the change in temperature with respect to pressure of a pure solvent. So here when this curve reaches the point B, that is when it becomes exactly equal to the atmospheric pressure, the pure solvent begins to boil. And when a solute is added to this pure solvent, that is when it becomes a solution, we can see the vapor pressure curve, that is CD. Here the vapor pressure is lowered. That is why the curve CD is below the curve AB. When the solute is added, the vapor pressure is lowered. But we can see that the boiling point is increased. That is, when the vapor pressure reaches the point D, the solution will begin to boil. So at the point D, the vapor pressure of the solution becomes exactly equal to the atmospheric pressure P. So there is a difference between the point D and B. Here we can see the temperature difference, that is delta TB. Here the point T0 in the temperature axis denotes the boiling point of the pure solvent, and the point T1 at the temperature axis denotes the boiling point of the solvent. So this temperature difference between T0 and T1 is actually the elevation in the boiling point, which is represented as delta TB. Okay, the subscript B represents the boiling point. And this boiling point, this elevation in boiling point is found to be proportional to delta P, that is the lowering of the vapor pressure. So this delta TB is actually proportional to this difference, that is delta P, the lowering of vapor pressure. And this lowering of vapor pressure is in turn proportional to XB. We know that XB is the mole fraction of the solute. So the lowering of vapor pressure is proportional to the mole fraction of the solute. So therefore the elevation in boiling point is also proportional to the mole fraction of the solute. That is delta TB is proportional to XB. So here if we are removing this proportionality, we can introduce a constant K. So delta TB is equal to X into is equal to K into XB. Here K is a proportionality constant, and we know that XB, that is the mole fraction of the solute, B is equal to number of moles of solute divided by total number of moles of the solution, that is NB divided by Na plus NB. And also we know that NB is equal to WB by MB. Similarly Na is equal to WA by Ma. Therefore substituting these terms in equation, we change the equation to the following format, that is delta TB is equal to K into WB by MB the whole divided by WA by MA plus WB by MB. Now for a dilute solution, we are considering the mole fraction or the number of moles of solute to be negligible in the denominator part, because the major portion is only the number of moles of the solvent. So we can neglect the number of moles of solute in the case of a dilute solution. Therefore, the equation changes to delta TB is equal to K into XB, that is K into WB divided by MB divided by WA divided by MA. So here we are rearranging the equation and we get K is equal to WB by MB into MA divided by WA. So this denominator part we are changing it to the numerator part and rearranging the equation. So here again this term, that is WB divided by MB, is actually NB, that is the number of moles of B. Here WB is the weight of the solute B and MB is the molar mass of the solute B. So here WB by MB is equal to the number of moles of B, that is NB. So substituting NB in this equation, we get delta TB is equal to K into NB into MA divided by WA. Again, in this equation, the term NB divided by WA, this is actually representing the molality of the solution, that is number of moles of solute divided by the weight of the solvent. This is actually molality, which is represented using the small m. Therefore again this equation changes to the form delta TB is equal to K into MA into small m, that is molality. Here the terms K and MA, that is proportionality constant K and the molar mass of A, molar mass of the solvent part is constant. So we are converting these two terms into another constant, that is KMA is actually taken as another constant. It is replaced by another constant called KB. So delta TB is equal to KB into M. This is the equation we are obtaining. Delta TB is equal to KB into M. Here the constant KB is called molar elevation constant or molar ebullioscopic constant. This is the name of the constant KB, molar elevation constant or molar ebullioscopic constant. So here from this equation we can understand that the elevation in the boiling point, that is the increase in the boiling point of the solution form, is actually proportional to M, which is the relative number of moles of solute, and therefore this is a colligative property. So in the above equation we are trying to get a definition for this molar elevation constant or the molar ebullioscopic constant. For that, if you are considering the molarity of the solution in the standard state, that is in the unit state. So in this case if you are substituting M with 1, then delta TB will become exactly equal to KB. So we can define the molar elevation constant or the molar ebullioscopic constant KB as the elevation in the boiling point, that is delta TB, of a solution containing 1 mole of a non-volatile solute dissolved in 1 kilogram or 1000 gram of the solvent. So this is the definition. Molar elevation constant of the solvent may be defined as the elevation in boiling point of a solution containing 1 mole of a non-volatile solute dissolved in 1 kilogram or 1000 gram of a solvent. So here the Kb values are expressed as degree per molarity. So degree, it is the unit of the temperature, and m, it is the molarity. Therefore the unit of Kb is K by m, or degree Celsius divided by m. Here K is Kelvin. Kelvin divided by molarity. Now let us calculate the molecular weight of the solute. So just like in the case of lowering of vapor pressure, here also in the elevation in boiling point also we are able to calculate the molecular weight of the solute. For that we have to take this expression again, that is the molality of the solution. The molality of the solution denoted using small m is equal to Wb into 1000 divided by Mb into Wa. This is known. So Wb is the weight of the solute and Wa is the weight of the solvent, and Mb is the molar mass of the solute. So this is the expression for molality, and substituting this expression in the above equation, that is delta Tb is equal to Kb into m, we get the following expression. Delta Tb is equal to Kb into Wb into 1000 divided by Mb into Wa. Here we have to calculate the molecular mass of the solute, that is Mb. Therefore we are rearranging the equation as Mb is equal to Kb into Wb into 1000 divided by delta Tb into Wa. Here delta Tb is the elevation in the boiling point. Now if we know all these values, that is Kb, Wb, Wa and delta Tb, then we can calculate the molar mass of the solid substance which is added to the solvent. So here is a few problems, that is problem number 2. Here you are asked to calculate the molar mass of the solute, and the following quantities are given, that is a solution having 7 grams of non-volatile solute in 250 grams of water boils at 373.26 Kelvin. So here you are given the mass of the solute. Mass of the solute is 7 grams and mass of the solvent is 250 grams. We know that the boiling point of water is actually 100 degrees Celsius. So that is 373 Kelvin. So when this non-volatile solute, 7 grams of non-volatile solute is added to water, the water's boiling point increases to 373.26 Kelvin. So this is the elevation in boiling point. So the difference between 373.26 and the normal boiling point of water, that is 373, is actually the value of delta Tb, that is the elevation in the boiling point. Now we have to write the expression for the molecular mass. We know this is the expression Kb into Wb into 1000 divided by delta Tb into Wb. We have to substitute all the known values in the equation and we can finally get the molecular mass of Mb, that is 56. Let us see problem 3, that is the boiling point of pure water is 373 Kelvin. Calculate the boiling point of an aqueous solution containing 18 grams of glucose in 100 grams of water. So the weight of solvent, that is water, is 100 gram and the weight of the solute, that is glucose, is 18 gram. So WB is 18 gram and WA is 100 gram. And we also know the boiling point of pure water, that is 373 Kelvin. And the molecular mass of glucose is also a constant, which is a known value, that is MB is 180. Now we are asked to calculate the elevation, the elevation in the boiling point. So here the molar elevation constant, that is Kb, is given in the question, that is 0.52 Kelvin per mole. Therefore, we can rearrange the equation as delta Tb is equal to Kb into Wb into 1000 divided by, here there is a small mistake in the question. Here you have to put the value of Wb here, that is 180. So the Mb here, not delta Tb, Mb. Okay, so Mb into Wa. So here delta Tb will be 0.52. That is the elevation in the boiling point, that is 0.52 Kelvin. Now you are asked to calculate the boiling point of the aqueous solution, that is the boiling point of the pure water plus the elevation in the boiling point. So the boiling point of the solution will be the boiling point of the solvent plus the elevation in boiling point. So 373 plus 0.52. So this is the final answer.